using. So that is all the results, and hoping that I think all of these will be producing a lot more results and conclusions in the next couple of months. So looking forward to telling you about those in the future.
Thank you. Questions or comments? Is there anything online? Any questions or comments online? No.
Thomas Stuber, University of Arizona. If you're talking about micrometeorites, how large are they for you, and how large are your test particles in the lab?
Sorry, the test particles are much larger than the real ones because we can't get up to the speed that the real ones are. So we have to try and mimic the energy. The real particles are much larger. I don't remember the exact size, but in terms of their impact on the observatory, we think even the smallest ones could potentially be damaging or could at least disturb the wavefront error dynamically. So we're looking at the entire natural spectrum. Even lower than is really well known because other people haven't had to worry about the smallest particles.
Thanks. Any other questions or comments, anyone? All right, let's thank our speaker again. Okay, our next speaker is filling in for Colleen Maurice Redding from JPL. I think everybody knows you already.
I can say.
And you're going to be telling us about microthruster technologies. Thank you.
Hello, my name is John Ziemer. I'm actually now part of the HWO project. I'm the pre-formulation architect. But in my previous life, I was the cognizant engineer for a little thruster called the SD7 DRS polar thruster. NASA about 20 years ago decided to start investing in drag-free technology, and one of the things they decided that was important were both the control laws, but also the actuators, if you will, for the spacecraft, to maintain a drag-free environment, meaning that against the solar pressure, these thrusters would be pushing back and holding the spacecraft in a drag-free way. Now, what does that mean? Solar pressure is something like 7 micronewtons per meter squared, right? So I'm from Minnesota, to give you an analogy. That's about the weight of a mosquito. Not even that, a weight of a mosquito's wing. It's landing on the spacecraft if you want the resolution you need in order to maintain that drag-free environment. And that was specifically for LISA. And so LISA is on those 10 picometers, right? So LISA has already worked on how do you go and demonstrate a stable system down to that 10 picometer level. Well, the first thing you do is you try to have an observatory that is stable to 10 nanometers. And so that's what these thrusters were designed to do. So I'll be talking about these a little bit, and I want to recognize Colleen. She's now our leader for this effort. Nate Demons at Busick is our industrial partner. And then we also work with University of California, Irvine, and back in the day, UCLA, to help work on our models. Next slide, please. Okay, so I'll talk about, for those of you who don't know, this is a science conference, right? So I'll talk a little bit about some of the electrospray fundamentals. I'll talk a little bit about the thrusters that were demonstrated on LISA Pathfinder. LISA Pathfinder is an ESA mission. I know Paul McNamara was here earlier, but if our ESA colleagues are in the house, then again, appreciate all the work and help that they did to host our payload on their spacecraft. It was one of the few times they actually let us take control of the whole spacecraft. So during those experiment times, it was really exciting. Then we'll talk about the next things that we did was, instead of a tech demo, which is a single string device, we had to create something that'd be worthy of a flagship, dual string and everything else that goes along with it. That had to change the design a little bit. So we worked on that for a little bit for LISA. And then now lately, after the LISA project decided to continue with the cold gas thrusters from Europe, we've been funded under SAT to continue work on long duration tests to make sure these thrusters can actually survive for at least 7 years, if not 10 or 20 years. Okay, next slide. Okay, so what is an electrospray? It's one of the most finely controlled electric propulsion devices you can have. Basically, you have a semiconductor or conductive fluid being flown up to an emitter. The capillary forces that are holding it back, these are very small scales on the order of 100 microns or so in diameter. The capillary forces holding back that liquid conductive propellant are balanced by the electrostatic forces that you're applying with a voltage anywhere between 1,000 and 8,000 volts there on that first grid. And then that also accelerates those charged, as after they come to the end of the jet and they're separated off, that accelerates those charged particles out into the beam. Because the charged particles at the base of the beam are so close together, they spread out. They have their own electrostatic pressure that sort of pushes them apart. But the good news is that's very predictable. And in fact, you can shape that beam by shaping those electrodes. And so you can set up basically a way of making sure not only do you have a precise thrust by controlling the voltage and the flow of the material to the tip, but you can also control where the beam goes and make sure it doesn't contaminate any other of your surfaces. Okay. But there is a problem. There is a minute flux, a very minute flux that ends up at wider angles and ends up starting to impact the grids. Now, on ion thrusters, is an erosive process, right? So if you've worked on any Hall thrusters or ion thrusters, they actually have to deal with a lot of erosion. For our particles, they're not actually, they're liquid. They're groups of molecules. And so they don't actually sputter the material. So we decided to create a way of absorbing them like a sponge. So this is actually a porous material that we use for the grids. And so when the propellant hits that, it soaks it up like a sponge. And so then our lifetime isn't set by how fast it erodes. It's set by how much capacity do we have to suck up that extra propellant. And so it also depends on operating conditions. The more charge you try to put through, the broader the beam. So if you limit yourself to the amount of current that's in a single emitter, you can basically not hit the grids at all. And you can almost infinite lifetime as far as that's concerned. Okay, so yeah, next slide. Oh, sorry, go back one. The other thing I wanted to mention is what we didn't understand during SD7 was how important the test facility was. We tested these, you have to test these in vacuum, obviously. But what we didn't understand is that when these beams would hit the facility wall, man, they would make a perfect circle. You could see it right on the facility wall. What we didn't understand was how much flux was actually coming back to the thruster. And in fact, looking at some of these old pictures, you can see sort of this brownish color. That's actually stuff coming back from the facility. So one of the things that we've done over the last few years is understand exactly how to design the beam target so that doesn't happen. That was influencing our life tests and actually making it look like we had shorter lifetimes than we actually did in space. So that was an interesting problem as well. Next. Okay, so SD7 DRS stands for Space Technology 7. DRS, for those of you who, 20 years ago or so, that was the NASA New Millennium program. Raise your hand if you remember New Millennium program. Okay. So it was, like I said, it was hosted on the ESA Pathfinder spacecraft. On the ground, we demonstrated a 3,478-hour test. On orbit, we demonstrated over 2,400 hours on 8 different thrusters. These were all intended to keep the attitude of the spacecraft and the position of the spacecraft, more importantly, because we had 2 free-floating test masses, to below 10 nanometers per root hertz. Next slide. So that's, to give you an idea, again, I love scale. To give you an idea, DNA helix is 2 nanometers in diameter. Right, so imagine a spacecraft being stabilized to about a DNA helix. Okay, that was the goal. Okay, again, here you can see this sort of cartoon. The solar pressure, the photon pressure hits the spacecraft. The thrusters push back against that so that those 2 test masses can be maintained within picometers, 10 picometers. But there's a transfer function there. They have their own control system there that maintains their sort of 1,000-to-1 reduction from the spacecraft motion. Next slide, please. Okay, so the system had 4 thrusters on it. Looks like an attitude control thruster because that's what it is. Each thruster has its own tank because they all have to operate at different voltages. The propellant's conductive, so it ends up going back into the tank. So you have to isolate the tanks. This is all tricky, right? We were isolated up to 10,000 volts for various things. Each thruster had a single string valve to it. Of the 4 thrusters, so we end up with 2. And then 1 spacecraft computer to run both of them. Next. One of the most important things that we did, it was really challenging on the ground to measure this 0.1 micronewton or 100 nanonewton resolution. We designed special facilities for it. We thought we demonstrated, but at the lowest frequencies, it was almost impossible. So one of the things we really wanted to do was demonstrate that this model we had for how much thrust the thrusters produce worked even at the lowest frequencies. And that really couldn't be done on the ground. So it's going to be interesting for us too on HWO when we think about how we demonstrate these 10 picometers and we get down to the lowest frequencies. You know, how do we validate our models on the ground so that we can show that this whole system is going to work up in orbit, right? That's going to be very challenging for us. But that's what we had to do on Pathfinder. So it's not that it can't be done. It just is tricky. We did show that this model worked on the ground at higher frequency, and then on orbit we showed that it worked over the whole frequency range. Next. These are a list of all the different tests we did on orbit. Next. So here's a result. This is here you can see this is a 10 nanometer scale here to here. So this is much smaller than nanometers. How do we measure nanometers in space? Well, we have these free floating test masses that were designed to measure gravity waves, right? So these test masses are incredibly sensitive. They can measure down to 10 picometers, so that's a very valid measurement. If you look then at the way we're able to the position as a function of frequency, you can see even at the lowest frequencies, we're able to maintain our requirement and just have just about a couple nanometers per root hertz of disturbance noise on the spacecraft residual after the thrusters. Next slide, please. We also did a test where we injected a signal and tried to make sure that we are also meeting our own thrust. We basically turned the spacecraft into a thrust stand, and this is the signal we injected here so that we could see that we are meeting our thrust noise profile down to 10 to the minus 7, 10 to the minus 8 newtons per root hertz. So again, we're talking about mosquitoes' wings, not even a whole mosquito. Okay, next slide, please. The other fun thing that we got to see is micrometeorites hitting the spacecraft. And so when a micrometeorite hit the LISA Pathfinder spacecraft, the attitude was changed enough so that the thrusters would have to respond. And so that's the peak you see here. This is a typical data set of us operating. You can see we're very stable over time. And then a micrometeorite comes in and the whole thing shakes and has to adjust. Shakes meaning, we're operating at a couple extra micronewtons or something like that. And so there's a European paper actually that has a database of all the different micrometeorite impacts and gave us a very good database of the micrometeorite environment in an Earth trailing orbit. Next. So after we got done with that, very successful, met all of our requirements. We moved on to the next phase, which was to make the system redundant, not just a single string. So we started adding extra valves in series and then the whole system in parallel. We also started understanding a lot more about the lifetime of the thruster, started designing the electrodes. We had a lot better tools for modeling the thruster. This was over the span of the last 20 years, right? So there's been a lot of progress since we first got started back in 2005. The whole flow control assembly, this has all been assembled and tested multiple times now. You test it with nitrogen first, then you can fill it with propellant. The thruster head from SD7 hasn't really changed. The key thing here is that if you want to go to higher thrusts, obviously HWO will be a much larger observatory than what LISA Pathfinder was. LISA Pathfinder was about the size of one of these tables. You're going to have to go up in thrust, right? And so each emitter is a certain amount of thrust. And so if you want more thrust, you just pile on more emitters. Now, since then, people have becoming, not just Busick, but other companies have come up with ways of microfabricating these arrays. And so now you see arrays of hundreds of these emitters in single chips. And so the technology has advanced way forward from these conventionally machined emitters. So we're continuing to use these just because we understand them really well, but that's really where the technology is headed since then. Next. So we've been partnering with UCLA and UCI in order to do modeling of the plume. These are very careful modeling and measurements then to validate those models, getting down to something like mass fluxes of nanograms per second per steradian in order to validate that the lifetime of these thrusters will be, the models are matching our results. A lot of work here. I don't want to go into all these details. I don't have time to, but really interesting physics of understanding how these things actually operate. These are all physics-based models of how the thruster plumes interact and propagate downstream, and now the measurements and the models match very well. Next. If you use those models then to extend out and say, basically in worst cases, if you take on some of the measurements there's still a lot of uncertainty, right? If you're trying to measure nanograms per second, there's a lot of uncertainty in those measurements. And so those uncertainties lead to big bands. But here we're talking about, sort of years of lifetime. 7.5 was the objective for LISA, but some of our models were predicting 100 years or even 1,000 years. I mean, in other words, just the beam wasn't hitting the grids at all, right? So, but in the worst cases, at the highest operating currents, we were seeing, even then we were able to, still stay on with 7.5 years lifetime with the grids that we designed. Next slide. Okay, so the SAT program, the latest work is basically continuing work on that 9 emitter design, even though we'll know we'll need more emitters, but everything you can learn from those 9 emitters, you can scale up to a large emitter. So this is sort of a tier 5 scalable demonstration, if you will. Here we're going to be going to starting a test here. Actually, the test readiness review is next month. And we will be running it for as long as we can, basically, as long as funding will take us, we will continue to run it. Thanks. We'll continue with our lifetime model development validation, the facility and everything else like that. We have the model, including the beam target now, which is really important. We found that's a really critical thing to include. And then we'll be propagating our uncertainties with using this NDIA uncertainty quantification tools to make sure that all the different parameters that we have go into our lifetime prediction. Next. Okay, so how do you extend lifetime? This is, imagine that the grids fill up over the years. This is sort of a cartoon of a rate. Go ahead. Next. This is where, we say the grids can only be filled up this full before they start being too full. Next. So that gives you a lifetime. Says, okay, if you have that much hitting the grids and that much capacity in your grids, then you get a 4-year lifetime. Next. This was our requirement, right? So we blew away our requirement the first time around, but we really didn't know enough to know. The LISA requirement was 7.5 years. Next, so what that means that we decrease the beam impingement, so decrease the rate at which the beam actually hits. Next, we increase the grid capacity. Next, and then we decrease the uncertainty in the predicted lifetime, and then we'll get to a 10-year lifetime. That's our plan. So we've done all of those things. Now we just have to demonstrate it. So literally, the long duration test is going to start next month. Next. Okay, fast forward. This is the last slide. I'll leave it up here for you. Basically, we want to show that this scalable approach is going to work for future observatories. The same kind of requirement of getting down to an observatory that has, sort of 10 nanometer stability will lead to 10 picometer stability where we need it to be otherwise. So it's really creating a very quiet observatory. In LISA, when we were doing it, we were also looking at attitude, and we thought we could get down to 10 nanoradian kind of levels of stability with these thrusters and these noises. We want to scale up and make sure the system is built for a flagship mission. Fully redundant and basically demonstrate. So we'll start the test. Thank you.
Thank you. Okay, Bill, we've got a couple of minutes for questions or comments.
Hi, this is Edwin from RIT. It's a great talk. I'd never heard of this technology before, so my question might be coming from a place of ignorance, but what is the, power requirement comparison with regular thrusters with that just propel gas?
Yeah, it's a great question. So the normally when you hear about electric propulsion thrusters, you hear about kilowatts and things like that, right? Well, they produce, millinewtons to almost a newton of thrust. And so the thrust to power actually for these thrusters is quite high. And so in the beam itself, there are milliwatts. The thruster itself, the biggest overhead is actually for the avionics that run them. And that processor takes 5 watts. So at the end of the day, if we scale this up, it's probably like a 20-watt system or something like that. It's really small. And the propellant is a liquid, so it's stored, like for LISA, we were thinking that we needed about, for each thruster head, we needed about 1.5 liters of propellant, to give you an idea. So it's really compact and not much power.
Thank you for meeting me halfway.
Sure. So 2 questions, I guess. One is, what's the practical propellant packaging lifetime limit?
Yeah.
And then the other thing for lifetime is there not a way to have a deployable secondary plate to refresh that catch plate?
Oh, you mean
No, well, not servicing, literally have a secondary plate hiding behind your first anode.
Yeah.
That you then release and cover up the old one.
Oh, that's interesting. Yeah, we hadn't thought about any mechanisms or anything like that to replace the propellant. It's actually pretty easy to increase the capacity. At the end of the day, we were kind of limited by some manufacturing and available materials. Now you can get this porous material in any size you want and all sorts of things, right? So we could just increase the grids if we had to. The other thing we can do per emitter is just to reduce the maximum current, and then basically we'll just never hit the grids. You just need more emitters then. So we do need to do a scaling exercise for HWO based on the thruster levels that we need to figure out what size this thruster should be, or whether we should go to one of the new MEMS approaches to manufacture the emitters or something else like that.
Thanks.
Yeah, thanks. Doc.
Okay, let's thank John again. Thank you. Okay, and our final presentation in this section is by Sebastian Rabien, I hope I pronounced your name correctly, from Max Planck, who's going to tell us about parabolic membrane mirrors.
Many thanks, and good afternoon to everybody. So that may be a bit special talk here, since it's not so much about adding something to HWO. It's about very, very large telescopes that might at some point in time building out of membranes. So I not come across Atlantic now to tell the HWO exchange, please, your primary. It's more about the future. Yeah. Please next. And maybe, there's a science case to the left you see, which is maybe the future. Yeah? HWO will look at that planet in a single pixel. You do photometry, you do spectroscopy, but then, after that, some point in time, you want to see this, no? Lights at the dark side of this planet. Since this is biosignatures, I don't need to model that. Yeah? And if we want to see that at some point in time, what you need, it's an array, a big array in space, it's kilometric. Yeah? And the single building block needs to be a 20-ish meter telescope, so something big that gets this planet within an hour before it rotates to get the flux. Yeah? So maybe we want to be there at some point in time. And actually, that's as well to the right, there's a usual plot, sensitivity that counts. Big telescope. If you go to a 20-meter telescope, that outperforms then every facility that we have now by a factor of 100. And that's huge. That's a big factor. Next, please. Well, and that's the talk about how to get a 20-meter. You need a super lightweight primary. You need lightweight structure. You need to pack it in the launcher. Yeah? You need to shape the optics since it will be lightweight. It will be all adaptive. I'm absolutely sure. And next. Why not try it with thin reflective membranes? And next, there have been quite some attempts in the past. A lot of things in the radio, some worked, some are already now as well in development for big antennas. And there have been tries in the optical, let's call it like that. Well, 20 years ago, there was quite some rush, actually. There were publications and conferences, etc. that didn't all lead really to a success of a big telescope. Nevertheless, since I considered that still to be a really compelling concept, and we tried it again. Next one, please. And that's actually how we attacked it. Yeah? Let's make a shape which is perfect, a parabolic perfect shape. And we took a very classical thing. Let's make a container with a liquid in, let's spin it, and this gives you a perfect parabolic shape. That's well known. Liquid mirror telescopes operate like that. So 120 years old knowledge. What we did, we deposited a polymer on this rotating container. And this polymer then finally serves us as a membrane. And if you go big, that will not be so easy. And actually, it will be wind, dust, curing, shrinkage, etc. All that stuff that then destroys your optical shape. Nevertheless, next. With a vacuum CVD process, we could kill a lot of that. Yeah. Next one. And this is actually our test chamber. It's relatively simple. Yeah? That is a vacuum process. We use perilene as a polymer, which is a known material as well. The process is known for since 1960 or something. So we combine the things. Yeah? Very old rotation thing, very old polymer process. And together that forms a new, very nice process to shape membranes in the vacuum. Until now, we have relatively small units, 30 centimeter diameters, and that serve us as test bed. And let's say, but what we think is that the process could be scaled up easily. Yeah? You can make this as big as you can build a vacuum chamber. Yeah? And I think you can make it very big. Until now, we growing membranes up to 200 micron thick. That serves us let's say, in terms of handling and in terms of what I will show next. That's a good measure, actually. Next. And if you, after growing it in the chamber, you apply a reflective coating and you wash the liquid away, you put it to the closest line to get it dry again. And at the end, you put it in the optical test tower. Next. That's super simple as well. As you would usually do it, you go to the radius of the membrane, you measure it with a Check-Hartmann sensor, and you check the shape. And actually, when we first got those images on the first membranes, we've been super happy since we can measure it optically. That was not expected at the beginning, really, since it's super thin material, it's deformed for a lot of reasons. But if you can measure it optically, you can find a way to correct it, to make it really good. And that was the goal. Passively, 2 microns RMS on a 30 centimeter unit. Okay, that's not really an optical telescope, but then we found a process actually that helped us to adaptively shape it. In former times, people thought, and I thought it at the beginning as well, let's make it electrostatic. That's a classical thing, but that's complicated. You add a backing structure, you add high voltage. That's not so easy. But we found as well in discussion with colleagues here a way to do it differently. Next. Actually, we found a way to tune it with radiation. So what we do is we shine a light source onto the membrane. Parts of it is absorbed. And basically, since the material has an CTE, the material expands. And we do that locally. We use a DLP, and we shine locally where we need a band in one direction. We decrease the intensity if we want it in the other direction. So the whole thing is biased, basically, with some radiation. And then you can, like with a normal adaptive mirror, you can go both directions. And that worked out astonishingly well. But you see here's a test setup. And actually, so the good thing is we don't touch the surface. We don't have a backing structure. And actually, we add minimum white to the whole system. That's a projector. Basically, I add somewhere behind my telescope. And that was me trying that out. With the setup you're seeing here to the lower right, to the middle, and illuminate from the front. In the lab, that's easier. And actually, that's the result on the next slide. Since we have a feedback, we can build an adaptive optics loop. In that case, was a zonal loop with very slowly decreasing the RMS here of the membrane. And at the end, we end up with something which next is basically a 50 nanometer RMS surface, which brings us into the range where we wanted, a visible light diffraction limited telescope. That's where we are, more or less, here in the adaptive control. And next. Now, how to mount the whole thing. Yes, that's as well something which is not so easy. And that some recent study has started. It's very preliminary here, what I show here. But we think we can wire that up with a proper mounting border. We think we can put it into some wires, which adds as well very little weight to the whole system. And as well, if you do it right, which is not yet shown here properly, but I think we can distribute the load nicely around the border of the membrane. And as you see to the lower left, I think you can then tension the thing up and bring it into proper shape. And it's a bit of a study which comes on the next slide. Next. We're looking a bit what it means if you have a flexible membrane. Next. Okay, video didn't work, sorry. It was a deployment. That's how we imagine it could look like in an observatory. That's a toy model for the moment. And the toy model mainly serves how much space does such a system really need if you pack it, and how could you deploy it. And that's where we're actively working on it. And we did this little 3D printed thing you see on the bottom, which serves as a playground on how to deploy things, how to get it into the proper direction, and actually without damaging the mirror. Where actually in this toy model we already have one, and you can see here this is a real rolled mirror. It's not a Mylar thing. Okay, so let's say it's a toy model, but if you take this toy model serious, next, then you could roll a mirror up. It takes very little space at the end. So it's approximately a 4-meter diameter footprint for a 20-meter size telescope. So this means in a small 5-meter fairing, you can place one. Or taking here's a SLS Block 2 cargo. Yes, that's a good fairing. You can place 3. And I think then we are there to go for arrays. And next. That's next steps. Very quickly, we're looking for different coding possibilities to absorb more of the control power, since it's not very good if you reflect 95% of it. And you're looking into a model control basis, which seems to be progress very well. And actually, then looking at the structural model and doing a bit more calculations, modeling with the partners which are on here. And actually, there's a lot of dots here. Yes, there's so much to do. That's next, please. And thank you. I conclude. We've been doing some mirror, but there's a lot to do still. Many thanks.
Thank you for an interesting talk. I see some questions online.
Yep. So Michael Best asks, he says, really interesting talk. Can you share a bit about what forms of radiation are used or most effective for the radiative adaptive shielding technique?
So for the radiative shaping, we would use in reality a narrow line source, be blue, green, or something that you easily can stop at your science instrument. Go to the UV, maybe with the material not super good, but you make the narrow band, you use the DLP with it, or if it disturbs your science band in one go, you could have 2. So switch. That's
Thank you.
As radiation can be used to improve the shape, is there any expectation that it will be sensitive to radiation in space, changing the shape over time?
Yes, sure. So this is a cartoon. This thing must hide behind a perfect and very good sun shield. On the other hand, since we're controlling it with radiation, if we hide, let's say, the kilowatts away, please go away. But let's say there's a remaining gradients over the telescope, etc. You do with your active control. So you keep your mirror everywhere at the more or less same temperature. So.
Thank you.
So was the initial control demonstrated done in air?
Yes.
So has there been any thought to how the change in the overall thermal boundary conditions are going to affect the radiative control that you're applying for maintaining a complex gradient over the surface?
I would love, let's say, for a demonstrator as well to go into vacuum. You may have seen that the control loop converge at some point and has some spikes. These spikes, that's all air in the lab, so that's disturbing. You accumulate some energy bubbles and that you see in your control. So I think in vacuum, only things can get better.
Okay.
Thank you for that interesting presentation. I missed a detail in the rolling up idea. If you roll it up, it's still 20 meters tall, right? So you have to fold it also, and then does it develop a crease, and does that lead to optical distortions, et cetera?
Yeah, since there's not so many of these membranes, let's say at the moment, we tried the rolling, that works. and you can unroll without getting some ugly shape afterwards. And let's say to do it in two directions, I don't expect it's going to work very well. So you still would have a 20-meter tall thing, yeah? But either get a Block 2 cargo, a lot of stuff fits in, or since it's not so big in diameter, one could think of other means. Yeah? It could fit into a tube at the side of a rocket.
Okay, let's thank our speaker again. Thank you. Thank you. Okay, so we'll reconvene at 4:20. For the speakers that are going to present after the break, please go and check out your presentations up there. I do want to apologize to Alice and Brianne for the technical hiccups that we had at the start. Sorry about that. Let's thank all of our speakers from this section one more time. Thank you.
Joe, did you get some good questions?
Okay, welcome back everybody from the last coffee break of the day. So let's kick off with the last of our presentations. We'll start off with Coralie Niner from the Paris Observatory, who's going to tell us about the Pollux instrument.
Thank you very much. Hello, everybody. So indeed, I'm Coralie Niner from France, and I'm going to present an instrument that is proposed by Europe as the fourth instrument on board HWO. And on this slide, you see the name of all the members of the Pollux Project Office. Please wave, people can see you, look over there, all right? Jean-Claude, David. So all four of us are here. Don't hesitate to come and talk to us after this talk or any time until the end of this conference. Next slide, please. So in Pollux, we grouped the science cases into three themes: the stars, planets and exoplanets, and cosmic ecosystems. And you probably recognize that this matches quite well the four science themes that are on the left here from HWO. So that means that Pollux replies to the priorities set by the NASA Decadal Survey, Astrodecadal Survey, but it also replies to the priorities set by ESA Voyage 2050 and by the Astronet Roadmap. Next slide. So I'm going to give a few examples of science cases for each of the three themes that we have. I'm not going to go into details. I rather want to talk about technology today, but just to show you the breadth of what we want to do with Pollux. So for example, for stars, we would like to understand the impact of magnetic field on the formation of stars. So that's magnetospheric accretion. We would like to understand better the magnetic fields in massive stars, for example, in other environments with different metallicities. We also want to understand how they evolve, what is the origin of these fields. And another example is stellar spectroscopy in the local group and beyond. For example, chemistry and metallicity distribution for first and second generation stars, and many other things. And Ana Inés Gómez de Castro, who is sitting here, is the lead for this working group, so you can also talk to her. Next slide. For the planets and exoplanets, so first, we have science cases about the solar system, of course, but then about exoplanets, we want to understand, for example, the atmospheric characterization and escape. We would like also to understand the star and planet interaction, magnetic, but also others like tidal interactions. And we want to understand the composition of rocky planets. And again, many more things. Luca Fossati sitting there is currently the lead for this work package, but since he has become our project scientist, we will have to replace him very soon. Next slide. So the third theme, cosmic ecosystem, this is about interstellar medium, circumstellar medium, etc. It's about galaxies in all kinds of activity phases. It's also about the cosmological probes, for example, the polarization of the fossil radiation, the distant galaxies, gravitational lensing, etc. There is a poster by Julie Biederman that you can check on a massive black hole. And also there is a poster by the working group leader for this theme, which is Frédéric Marin. Next slide. Okay, so to answer all these great science cases and many more that I couldn't cite today, we've designed this instrument. It is a high-resolution spectrograph, high resolution meaning 100,000, and it covers a very, very wide wavelength range from 100 nanometer far UV up to 1.88 micron near infrared. And you get this whole range in just one shot. We have separated the spectrograph in several channels, but all channels observe at the same time. In addition, each of these channels is equipped with a polarimeter that is retractable. You can decide to also collect the polarization information. So it's not just a spectrograph, it is a spectropolarimeter. And you will get spectropolarimetry in one shot from the near infrared down to 120 nanometer. And then you have to use a separate channel, the far UV channel in green over there, to get polarimetry for the far UV between 100 and 123 nanometer. We do this because polarimetry in the far UV is a different technology, and also we would like to have a lot of photons, so we want to have a shorter path for the photons. Next slide. So I will not explain this schematic design, but it's just to show that the far UV channel is on the side for polarimetry, but everything else is in a row, so you get all the channels observing at the same time. Next slide. So to create this instrument, we had to develop several technologies. First of all, we've been working for a very long time already in Paris on polarimeters for the UV, near UV and mid UV polarimeters. This is now very well advanced. We're just finishing the full space qualification. And now we're working on the far UV polarimeter, and it's a completely different design, using only mirrors because we cannot use birefringent material in the far UV. You can check the poster by Adrien Girardot. Adrien, where are you? Over there. So you can also just talk to him or check on Slack because the poster is not on anymore. Can you just remove this window? Thank you. The next technology that we're developing are dichroics, because we have all these channels in a row to observe the whole range at one time. We're using dichroics to separate the wavelength range. And so we're developing this in collaboration with industry, REOSC in France, to have a wide wavelength coverage and at the same time a high efficiency. We're also working on UV gratings, because now we need not only high efficiency, but we need low polarization because it's a spectropolarimeter. Of course, polarimeters are very early on the path of the light, so we don't really care about polarization after in the spectrograph, but still, we will have to pass two beams of light of two orthogonal polarization, and we don't want one of them to be extinct compared to the other one because of the polarization of the grating, for example. Of course, we also need to work on UV detector for efficiency, and you will see the talk by Jesper Skotfeld over there. Thank you, Jesper. And finally, we recently decided to develop a UV Fabry-Perot combo. Why do we do this? Because when you work in the UV spectroscopy, you need to have lamps for wavelength calibration, and these lamps have a very low, very short lifetime. So you need to have many of them on board and change them very regularly, and we didn't like that, so we thought it would be much nicer to have a Fabry-Perot comb. Then we have a lot of lines, a comb, and also we just need one, we don't have to replace them. So this is something new that we just started recently. It's a collaboration between several countries. Next slide. So this is how the project is organized. It is led by France, but we have many European countries participating. Here you can check how well you know the European flags. So we have Austria in charge of the main electronics. We have Germany in charge of the focal station. We have third countries in charge of the various channels, Spain in the UV, the Netherlands, Switzerland. We have Italy in charge of the integration test and validation. And we also have Sweden in the data reduction processes, etc. Switzerland for the data center. So you see, we already have a very nice consortium of European countries, but of course this is still open. You can still participate. And also you've seen that the design is not completely finished yet. We're still working on trade-off. For example, what would be the exact cutoff in the near infrared? What will be the exact resolution of each channel? So if you would like to contribute either to the design or to the science, you're very welcome to join. Next slide. So how are we going to fund this instrument? Because it is a European instrument. Either it will be funded by ESA, the European Space Agency, through a call that we expect ESA to issue next year. It will be a two-step call. So we will know in 2027 if ESA is ready to fund Pollux. But if not, then the national European agencies from France, Germany, etc., can come together, make a consortium, and fund Pollux themselves directly without ESA. And of course, we can also be a combination of these two things. We can have part of Pollux funded by ESA and the rest funded directly by the national agencies. So again, if you would like to participate in products, if you have ideas for science cases that I have not mentioned or that are not in our documents, you're welcome to join and tell us what are the things you need, what you would like us to put in products to make your science really feasible with this instrument. And so you can scan also this QR code. Next slide, please. I will just leave it big like that during the questions, so that if you would like to join the consortium, the working groups, or anything, just scan this, and you will know how to do it. Thank you very much.
Thank you for a great presentation. Any questions or comments, anyone?
Hi, Marco Andoni from Mina Brera. Just a curiosity, so you say that you're going to use the Fabric Pro for the wavelength calibration, right?
Yeah.
So how do you, let's say, absolutely calibrating wavelength with the Fabric Pro if you don't have, let's say, the UV, Toron argon lines or whatever? So, I mean, if you have a drift, the Fabric Pro does not have the absolute.
Yeah, there are lamps that work in the UV.
Okay, so
that we have used on Hubble, for example. But
Okay.
the lifetime of this lamp is very short. So if we want the instrument to work for many years, we would need to have, I don't know, 10 lamps or 15 lamps on board and change them very regularly, because we need to have the lamps on very often for polarimetry. It's important for polarimetry that the wavelength doesn't change during a polarimetry sequence. That means we have to do a lot of wavelength calibration. And so we're using these lamps a lot. And so we didn't want to have on board, 20 lamps. And that's why we are free for this.
Yeah.
We will try it.
Thank you.
Hi, Rodriguez from Catholic University. So my question is about the FUV polarizer, the one for the 120 nanometer. What kind of polarizer do you envision? And what is the throughput of the polarizer you envision? Thank you.
Okay, so as I mentioned briefly, when we do polarimeters in the mid-UV, near UV, and further, we use birefringent materials. So these are materials that can just split two orthogonal polarizations. We do this for the modulator, and then we have an analyzer that separates the beams. When you go below, say, 120, there's no more material, so magnesium fluoride is the one that goes down the most. But below that, it just doesn't work. It is not transparent anymore. So we have to do everything with mirrors. So it's just reflections. So we have a K mirror, that's 3 mirrors in the K shape, that is the modulator. And then we have another mirror that is the analyzer. Having such a polarimeter is less efficient than the ones with birefringent material, because when you have an analyzer that is a mirror, you only get one of the two beams. So you're losing half of the light. And so that is also why our UV polarimeter channel is separated, because we want to cut down the number of surfaces before we reach the polarimeter.
Okay, is it silicon carbide?
Well, so the mirror, so go check the paper by Adrien, where you can see the design, but he has designed this polarimeter, and it is, the modulator is silicon carbide, but the analyzer is very specific with B4C and a layer of magnesium fluoride. And it is made in Spain by the Gold team in Madrid, especially for us.
Thank you.
Time for one last question. Anything online?
Not at home. Oh, wait, I got one. Okay. You have to put this switch. All right, here it goes.
Hello? Okay. Hi. So we have a question by Michael Best. How are you handling calibration across such a wide spectral range, particularly balancing sensitivity and stability between UV and near IR?
How are we doing the calibration along the full wavelength expression? So we have lamps for each of the channels. So in the calibration box, we have different lamps or combs, depending on the wavelength beam, let's say. And we send the right lamp to the various channels. So we do the calibration separately for each channel, but we have a requirement on the precision of wavelength calibration and on the stability of the spectrum on the image during the polarimetry sequence.
Thank you. Let's thank our speaker again.
Thank you very much.
Okay, our next speaker is Runa from INAF in Italy, who's going to be telling us about the Italian astrophysical community, what you folks are looking at.
Okay, good afternoon, everybody. I'm Bruno Briguglio. I'm an adaptive optics scientist at the Arcetri Observatory in Florence, in Italy, and I've been, let's say, selected to give this talk about the Italian community and their perspectives concerning a possible contribution to the HWO mission. So, next slide, please. Just give me a minute to present INAF. I'm a research staff at INAF. INAF stands for Italian Institute for Astrophysics. It's a government agency funded by government for the study of the universe and also the development of technologies enabling these studies. We are approximately, let's say, 1,400 people, mixing both scientists and technologists working together, and distributed across the peninsula in 16 observatories. We have strong synergies both with academia, university and other research institutions, like, for instance, the ENFN, National Laboratory for Nuclear Physics, and also industrial partners all across Italy and Europe, mostly electro-optics mechanics. And INAF teams are highly committed or involved in critical infrastructure, such as ground-based 8-meter class telescope like the RBT or VLT, and also ELT instruments, which can be very synergic in perspective for the use with the, in synergy with the HWO mission. And next slide, please. So I will give a spoiler of the presentation. The purpose here is simply for search for interaction tool. We would like to get involved. Spot the logo. We have posted yesterday and also posted today and tomorrow. So feel free to stop us and suggest way of interacting together to get the community involved in this nice project. I can stop here, but I have a few more slides presenting possible contribution lines. So next slide, please. So I would say we are in HWO mood. In fact, we just had a conference in Rome a couple of weeks ago with more than 200 people convening from all around, all across INAF in Rome. And okay, we are Italian, we're very confusing people. Everything is very fuzzy at this time, but there are three main points. And the fourth is that it's very early. We are at a very early stage to say that we are in a, let's say, finalized position. But next slide. The first point is that science community is very interested in the mission, and this will include not just exoplanetary science, atmosphere habitability, but also general astrophysics, spanning from star formation and population to cosmology and multi-messenger astronomy. And let me add that a key point here is that possible synergies with the current project may be exploited. For instance, everything concerned with the ELT, the Andes project, and the PCS project with ELT, and also project with the VLT, like Mavis. Next slide. We are discussing about proposing an instrument. There are many flavors here. Could be a focal plane post-coronagraph imager working from UV to infrared band, or a multi-object spectrograph. And this instrument could include astrometric and also polarimetric capabilities with variable range of spectroscopic resolution. And last point, next slide, please. We could get involved in supporting technologies with at least two areas of intervention. The first is to offer laboratories and metrology equipment for advanced testing. For instance, I work in DM technology, DM qualification, so my team could be of some help in assessing critical testing on the following mirror technology. But most important, we have research and development activities already going on since a few years concerning weapon sensor and control, optics and detectors, and this activity could be of some help in contribution to the HWO mission. So we did the exercise of listing our technology and try to organize them according to your very nice technological roadmap. Next slide, please. So that I would say that if we concentrate on the ultra-stable technology, ultra-stable telescope system, we could work concerning the advanced optic manufacturing, active mirror technology, and also extremely sensitive weapon sensing and astrometry. I mean, these are activities that we are already carried on in our laboratories since a few years, not specifically born for the HWO contest, but can transferred in time to this specific roadmap. Concerning coronagraphic system and high contrast imaging, we are working on waveform sensing and extreme waveform data management for post-processing and contrast enhancing in post-processing. And concerning high sensitivity UV, and also gratings. Next slide. Let me do some advertising. We have poster today and tomorrow concerning the last point. Poster in the virtual session, I think, concerning lightweight panels for primary mirrors, and the poster concerning gratings. So I encourage you to go down the poster session and look for them. And next slide. In the very last minute, I would like to spend 1 minute describing the activity of my team. We are working since 15 years developing high-performance I/O systems for 8-meter class telescope like the LBT and the VLT. For instance, the adaptive secondary at the LBT and VLT, and waveform sensors at the LBT. And now my team is working on the optical calibration of the gigantic 2.5-meter adaptive mirror of the ELT, controlled by more than 5,000 actuators. And since a while, we are focusing on the point of transferring this expertise, like downgrading the request of performance or moving them into the space domain. For instance, addressing the contrast requirement or the stability requirement. And we have two main questions in mind. If you have a waveform sensor able to deliver a very high frame rate waveform data, is that system able to produce a kind of real-time PSF reconstruction so that you can improve the final contrast and relax the specification of the system? And second point, if this system is coupled with a floating waveform mirror, which is virtually insensitive to thermal deformation, mechanical deformation, is this duo able to partly relax the requirement and improve the final contrast and final performances? We don't have answer. We are working. We have posters plus we have papers on the topic. So again, last slide. Summarizing, the point here is for both Italian collaboration, everything is finalized yet because we are Italian, so we take a lot of time in designing anything. I think someone is deciding where to go to dinner tonight, so I think the same story. But let's keep in touch, and I hope this point could be a starting of a good collaboration. Thanks.
Thank you. It's great to hear that Italy's in that HWO mood. Okay, questions or comments, anybody? Anything online? No? All right, in that case, let me say thank you again. Thanks. Okay, our next presenter is Kevin France, who's going to be presenting on behalf of Michael Honig, I hope I got that pronunciation right of his name, from JPL, who's going to be telling us about CMOS sensors for HWOs.
All right, thank you. All right. So I am pinch hitting today for the JPL detector team led by Michael Hike, who unfortunately were not able to travel to the meeting. And originally, Shirley was not able to travel to the meeting either, but now I see her here, and so I still find myself giving this talk. Do I control this?
No, the clicker doesn't work, so you got to flag me.
Slide, please. So I'm mainly going to report on recent results from a strategic astrophysics technology program that Michael led and that I'm a collaborator on. The idea here is developing advanced silicon detectors for use on HWOs. And so there's a couple of things going on here. First, the kind of progression from the total number of pixels required as we go from instruments of the 90s, with PIC2, up through missions like Gaia, Euclid, and then based on the LUVOIR design, the needs for the high definition cameras. So we're talking about a huge number of gigapixels now. And so we're going to need these things to be radiation hard, low noise, and fast readout, be able to work at the optical and the UV, and then the UV detectors optimized for visible rejection. So some of the goals that the project had when we started a couple of years ago were be able to develop 8K by 8K 3-side buttable devices with read noise down in the sub-electron level and milli counts per second per pixel. So, so next slide, please. Shirley showed basically the same slide in her talk, I believe, yesterday. So many of you are familiar with the MBE doping of the backside illuminated CCD devices, which make them UV sensitive. I'll show some relatively new results up here from the Castor team. So these were devices that were processed at JPL and delivered to Open University, and I believe Casper has a talk on this tomorrow, but showing really good QE results in the UV. Next slide, please. And then also the development of AR coatings for bandpass optimization. So, so an uncoated device, optimized device for the near UV, but without red rejection, and then some more work that they've done at JPL to increase the red suppression. And this is something that was designed for the Fireball payload. These are just recent, I believe from last year, some SPAE proceedings if you're interested in state of the art on those. Next slide, please. So, so one of the things that we first worked on was optimizing the electronics readout for this CIS 120 CMOS device, and already bringing it down from the out-of-the-box 8 electron read noise down to 3.8. And so this has got us into a position to basically do some advanced testing of these devices in real-world environments. And that's what I'm going to talk about for my remaining couple of minutes here. Next slide, please. So one of the things that we know about the CIS family of devices is that there are some questions about the gain calibration. And so we spent over 200,000 images to build this master dark frame, which will allow us to do the electron to DN conversion exquisitely on a per pixel basis. And so we're seeing now that for high signal levels, the gain stability is sub 1%. So this means that the detectors are very stable and calibratable. If you look at it in the lower plot here, this is basically seeing the same thing again, where the gain is shown here on the y-axis, and this shows the range as a function of the signal strength. And basically you stay in this kind of 1% uncertainty until you get to very low signal levels. Next slide, please. So the other aspect that we spent a fair amount of time on, this is really presenting Nathan Bush from JPL's work on this, is the cryo testing. So it's known that the degradation of the silicon devices is really related to charge trapping in the silicon, and that is temperature dependent. So at JPL, they developed a new cryo testing, irradiation testing facility. So I won't walk through there. You've all seen pictures like this. So they built this at JPL. It was stolen in the middle of the night. It looks like a movie from the 80s where they've created a heist. And they took this to UC Davis, did the irradiation testing, and then brought it back to JPL. Next slide, please. So they developed a process to actually track the charge traps in the device. I'm not going to talk too much of the details here, but basically they're able to find these things now and quantify the influence on the total amount of charge lost as a function of signal level. So you can see that for relatively bright things, the charge loss is pretty low over time, but for faint things, you can lose a couple of % of the total charge. Another aspect of this is essentially the dark calibration during the cryogenic irradiation. So we show here at the bottom 3 images: the unirradiated image, the irradiation at room temperature, and then the irradiation at about 200 degrees Kelvin. And this is the environment that it's going to work in. So this is the illumination level. And I'm not sure how well you can see it, but you can definitely see that there's an increase in the number of hot spots on the detector compared to the room temperature illumination. And if you squint real hard, you can also see that the whole image is fuzzier. So the total dark current came up after the irradiation, in addition to the increased hot pixels. Next slide, please. All right, so I just want to wrap up and talk about the work that's kind of ongoing now, and we'll be moving on to, hopefully in the next year or two, to actually use these things as real astronomical detectors. I think for somebody who grew up in the sounding rocket program, you never really learn how something works until you've tested it in an instrument that's supposed to do the thing it's supposed to do. So David Shimonovich from Columbia has taken one of the other CIS 120s and integrated it into his Chaz instrument, has taken it down to Kit Peak and has used it to actually do optical imaging on sky. So they have they did these runs early in 2025, and they have a new campaign coming up at the end of the next month, actually. Looking forward to the UV application, next slide, please, and getting these into space. These were the near UV detector baseline for the STAMP concept. Some of you might have heard me talk about this at SPAE last year. There's, after the HWO meeting at Space Telescope in 2023, a group of UV scientists and instrumentalists got together and said, what we really need to do is to test out all of these technologies in one really awesome small space mission. And so this is basically what the STAMP concept is essentially all of the driving UV technologies all built into one test bed. And so these UV CMOSs would basically be the near UV focal plane for that, if something like that ever happened. All right, and last slide, please. Right, so the next steps here are to continue to collaborate with Teledyne and SRL to develop yet further noise reductions. So this is kind of the longer range roadmap. Again, I believe Shirley showed this in a talk yesterday. Getting down to these sub-electrons or read noise over the next year or so, with the eventual goal being something that is pretty close to photon counting with very low noise after that. So if you want to talk more about the roadmap, we can talk about that after. All right, and that's what I've got. So I'm happy to take questions. Thank you.
Thank you, Kevin.
Hi, Jesper Scottfield from Open University. So I was interested in your radiation test you did at room temperature and cryogenic temperatures. Have you tested what happens after you room temperature annealed the cold irradiated device to the
warming it back up and seeing if it looks. I don't know the answer to that. I bet if Nathan were here or online, he would be able to tell you the answer to that. But I'll talk to him next week. Yeah. Okay. Then yeah, that's the best way.
Thanks. Steve McCandless, Johns Hopkins. I was very curious about the gain measurement. And I wanted to know, you may not know the answer to this, but maybe Shirley does. Oh, at what wavelength was that taken?
Oh, it's an iron 55 irradiation because it's a fixed number. Yeah, it's a very well-known number of electrons, so it's, yeah.
There's a question over here. Another one.
I was curious about the pixel format in terms of the pixel size. Have you tested different, maybe smaller formats, and would that improve some of the metrics?
So these are 10 micron pixels. The goal is to go to the 300 series. I think the 300 is also 10 micron. Yeah, so not yet, no.
Thank you. So not in this, are you asking this question? Yeah. Not in this series of work, but in the past we've done 2 micron, even 5 micron CMOS as well. Yeah.
Okay, and I think we have an online question.
Yeah, by Michael Best. How do you expect performance under deep field or long exposure conditions to evolve as delta doping and backside processing improve? Are there diminishing returns at ultra low photon flux?
Well, I think that the delta doping process is very robust and well understood process at this point. I think the related question here is at the ultra low signal levels. And so I do think it's, what's shown here is that there are some additional calibration uncertainties, but they're at the couple of % level. So at that level, you're kind of at the the calibration level of the instrument as a whole. And I don't see it being a showstopper at this point.
Okay, final question. All right, thank you, Kevin. So our next presenter is Maria Frutos, who's from Madrid, who's going to tell us about a lab to perform optical tests under vacuum UV irradiation.
Okay, thank you. Good afternoon, everyone. It is really a pleasure to show you what we are doing in the lab, at the lab, which is our ultraviolet laboratory. And I hope our work or what we are doing in the lab can be interested maybe for the habitable world community. So next slide, please. So who we are IGORA. We are a multidisciplinary research group with different scientific interests, but mainly focused on ultraviolet astronomy and also on the development of new scientific instrumentation. Our activities are carried out at the Joint Center of Ultraviolet Astronomy, which is located at the Complutense University of Madrid, the largest university in Spain. And we are also home to the network, to the European Network for Ultraviolet Astronomy, that is known as SNUVA. Next slide, please. So we are now involved in different projects and missions, but just to highlight some of them, I would like to talk about OL. OL is a small space observatory that has been recently approved by the Spanish Space Agency and is led by Ana Inés Gómez de Castro. So it will be provided with a Wi-Fi camera to map the Earth exosphere and magnetosphere while orbiting the Moon between 115 and 175 nanometers. And we really believe that the data that all will provide it will be instrumental in the preparation of future missions that will be devoted to the search and the study of Earth-like exoplanets. Most of my time goes to animals, a European Research Council funding project that aims to evaluate if it is possible to study the natriumeric stress amino acids and also their abundances in solar system bodies through the spectropolarimeter signatures. So animals will gather all the preparatory activities or associated with the Uriel mission. And Uriel is a proposal that has been recently submitted in the last ESA science program for an M mission. So it's a spectropolarimeter to study the emergency of life. It is inspiring the International Ultraviolet Explorer, and it will be able to work or to operate between 120 to 320 nanometers simultaneously in high low dispersion. And we are also working in different international collaboration, as you can see here on the slide. Also, we are part of POLUS, as Coraline has already told about. Next slide, please. So we are running not only the lab that I will talk about, but also a ground station, a small radio telescope, and a satellite ground system. Next slide, please. So going to details about the loop, our laboratory, it is divided into main parts. There is a contamination control area, which is provided with ISO 7 modular clean room, and also with an urn that is in turn provided with a laminar airflow module for more exigent manipulation regarding the use of ultraviolet light. And there is what we call like the dirty area of the laboratory, just for daily routines in the lab, and it is where we have our atomic force microscope installed. Next slide, please. So the lab has been already set and is growing, and the activities are now mainly divided in three main groups. Next slide, please. So we are studying the effect that far ultraviolet light can have on materials, especially on carbon-based materials. So for example, you can see here in the slide a photo where diamonds, nanodiamonds, these bright spots are being formed when we irradiate these carbon fibers with ultraviolet light. Next slide, please. But most of our time right now is devoted or goes to the development of instrumentation, especially under the framework of animals. So we are now designing a chamber to generate IC samples mixed with amino acids, mainly alanine. And once this sample will be formed, we will study these samples through the use of a microscope and a spectropolarimeter, both operated in the vacuum ultraviolet range. Hopefully after the summer, we will have the first result regarding the use of a reflectometer to study the surface of meteorite, of a collection of meteorite. And we have also set up an optical emulator that I will talk a little bit about it a little bit later. Next slide, please, just to study the optical properties of different optical elements. And we are also able, with our atomic force microscope, to study the surface of these optical elements in a nanometric scale. Next slide, please. So just to give you an example, a practical example of the kind of things we can do, regarding the optical emulator, we were part of a space telescope that was WSO, led by Roscosmos. So we were behind the development of the imaging instrument, the file camera unit, and in particular of the far ultraviolet channel. So this channel was provided with a filter wheel. What we have done is to design and set up this optical emulator that have allowed us to test in the lab these optical elements that were going to be on board this huge space, this big space telescope. Next slide, please. So this is how it looks like. It's an instrument that is very compact. So it is a vacuum chamber that is provided with different interfaces. For example, to mount a microchannel plate detector on the left, and also a turbo pump on the right. Next slide, please. And this is a view from the other side. So we have a deuterium lamp mounted from Hamamatsu, and also a pressure gauge just to monitor the vacuum, the level of vacuum inside the vacuum chamber. Next slide, please. So this is a view from the inside, just very briefly. The deuterium lamp is going to emit a light beam that is going to be reflected by the flat mirror to a first of-axis parabola, then back to a second of-axis parabola, and finally it will go towards the detector. But first it will pass through the optical element that we want to test. So these optical elements are mounted on a carousel, and we can, with a manual actuator, we can just rotate the optical element until the correct place. So that allows us to test up to 4 different optical elements without the need of breaking the vacuum, which is really nice. Yeah. So these are the measurement conditions that we can control. Under this configuration, we have been able to test 2 different magnesium fluoride prisms, and also calcium barium fluoride lenses manufactured by Technotica. Next slide, please. So it is important to take into account, before going to the result, the emission spectra of the deuterium lamp, also the quantum efficiency of our microchannel plate detector. In some cases, we need to use a neutral density filter to reduce the number of photons arriving to our detector. And of course, it's important to take into account the dispersion generated by the prism. Next slide, please. So this is the kind of results that we obtain. For example, this is if we place a slit in the output of the light beam. Then we place the prism, so we obtain the spectrum, but at some point it is saturated, and that is the reason why we have to place a neutral density filter on the bottom. What we can also do is to more or less regulate the intensity of the signal just by applying a gain on at the MCP detector level with an external power supply. Yes, please. So we have been able to compare the performance of 2 magnesium fluoride prisms, the one that was manufactured by Naoe in Mexico on top, and the one by Corp. And in that case, what we observed was like the prism from Naoe generates more dispersion, but also more diffuse light. And we thought that the polish of the surface of this optical element was behind this performance. So we asked our colleagues in Mexico to enhance this polish. And yeah, as we have an atomic force microscope in the lab that well is small, is just for routine measurement, we have also used it to see if we could study also the surface of some of the optical elements of our interest. So we have here on the right the topography that we have obtained while scanning a part of a mirror by Edmund Optics. And as you can see here, there is some scratches and maybe also some material that has been deposited. So we are also using our AFM to study the surface of these elements. So to conclude, I just wanted to show you the kind of things that we can do in our lab, that they can be maybe, as I say, interesting for you. Especially, I think it can be very interesting to use this kind of optical emulator that will allow us to test the performance of novel optical elements in full integrated system, in Taylor-like systems, because at the end we are using commercially available elements. It is true that a lot of interfaces and elements has to be manufactured ad hoc, but we know how to do it. So that is everything from my side. Thank you very much for your attention.
Thank you, Maria. Questions or comments, anybody?
So I'm not sure if I missed out on this part at the beginning of the talk. I think I heard like amino acids and ices being simulated at some point, or were you making actual samples of that? And then is there a concern that they could be destroyed in the UV?
Actually, as I said, this Animus project that has been recently founded and we are starting, what we are doing regarding the instrumentation is first we are going to generate IC samples with different amino acids mixed. So we will use enantiomerically pure amino acids, but also mixture of them, like one enantiomer and the other, 50-50. So then this sample will be processed, but also analyzed through the use of the microscope. So first with the microscope. So what we think is like the light is also going to process this sample. So the light is not only just to see, so it's also to see what is going on upon the radiation with the ultraviolet light, because it can, for example, dissociate, that is for sure. So we can maybe form some microstructure. So that is one of the goals of our projects. I don't know if I answered the question.
Yeah, thank you. I missed some portion at the beginning, so thank you.
Any other questions or comments? All right, Maria, thank you once again.
Thank you very much.
Okay, our next presenter is Enya-san, who's from ISIS JAXA, long-term friend and colleague, who's going to tell us about possible contributions from Japan to Habitable Worlds Observatory. Thank you, Enya-san.
Thank you, please. Okay, can you hear me? My name is Keigo Enya from JAXA. Title of my presentation is Japan's possible contribution to the HWO coronavirus. However, today we don't have final answer conclusion. So we don't have conclusion. So I would like to present about the current hour situation and current hour study. Okay, let's go. Next slide, please. Okay, this presentation includes three sections. The first section is programmatic station of JAXA's participation to HWO. Next, please. Okay. This slide shows JAXA ISAS HWO study task force team. And as a background, it should be noted that two JAXA representatives, one is Takahiro Sumi and the other is Satoshi Miyazaki, participated in the HWO start activities previously. Takahiro Sumi is there. And recently, the ISAS approved to create the ISAS HWO task force TF team in last December. And the main goal of the ISAS-TF is works in ISAS toward participation in HWO. And the information hub among Japanese communities that may participate into HWO. International coordination with NASA's HWO project office and as an institute as a POC of Japan HWO. The ISAS task force made its first visit to Goddard Space Flight Center in February of this year and had discussions with the HWO project office. Next, please. This is a member of ISAS task force. Task force member is in total. And here is I'm leading this task force, and the single camera is participating in this conference in person, and he is leading UV activity in our task force. Task force member consists of coronagraph, working for coronagraph people and UV people and 2 administrative people. And single camera will do presentation about the far UV, IFS and HRS activity of us. Next, please. Okay. This is a configuration of an organization. And as I think the task force, we made task force. I think it is evidence of JAXA is seriously and highly motivated to participate in to HWO. It's not by the individual scientist's motivation, but motivation of the space agency. This presentation is Japanese background for HWO coronagraph. Okay, next, please. Okay, firstly, I would like to explain about the project and the instrument level background. There are 3 backgrounds. One is speaker coronagraph instrument, SCI. The speaker is like this, outlook is like this, and as a planned space infrared, cryogenic infrared space telescope. And previously, we developed a coronagraph instrument to be installed on speaker like this. Observe the wavelength is 3.5 micron to 28 micron. And the target is not Earth-like planet, but Jovian-like self-luminous planet. So required contrast is not 10 to minus 10, but 10 to minus 7. But its instrument must work in the cryogenic temperature, 5 Kelvin. And this is a coronagraphic result of coronagraph demonstration I made. But finally, both the speaker mission and the SCI instrument were cancelled, unfortunately. However, we obtained experience in the designing an entire spaceborne coronagraphic instrument and the developing elemental technology such as a coronagraph mask. Next, please. Okay, secondary system level contribution is JAXA's contribution for Roman coronagraph instrument. The comprehensive substrate for coronagraphic mask, HLC and SPC, and optical component, fluorescent prism and imaging lenses for polarimetric mode, and R&D for compensator this is discovered. And currently, about 20 researchers join in the coronagraph community participation program, CPP, from JAXA ISAS. Okay, next, please. Okay, third one is more system level component is super coronagraph extreme adaptive optics SKEXEO. We call it SKEXEO, I know. And outlook is SKEXEO is like this. And role of SKEXEO is used for system level technology validation for HWO-J coronagraph. J means Japan. And ultimate contrast 10 to minus 8 for scientific observation and workforce development. And development of infrared photonic fiber-based spectrograph concept is ongoing. And these are thanks to, this slide is thanks to Olivier Guillon. Okay, next, please. Okay, furthermore, there are many component level contribution, potential contribution. There are many component level Cs, technical Cs in Japan. And indeed, in this conference, there are 6 poster presentations. These especially top two, by Ito, Satoshi Ito and Kojima, they are participating in person, and then there. Okay, next please. Okay, I cannot explain all of 6 presentations, and this is one of example. Global and chronographic mask, the multi-quadrant phase mask, created by Nishikawa and Naoshi Murakami, and like this. Okay, next please. Okay, let's go to the third section of this presentation. In this section, I would like to explain about the basic studies for HWO infrared coronagraph. Okay, please. Okay, firstly, science is the most important. Infrared coronagraph for HWO, science objective enough. This is a spectrum, near-infrared spectrum of planet surface. Oil, cloud, snow, water, or clear sky. Okay, there are important feature in exoplanet spectrum in near-infrared, for instance, HWO25, CH4, etc. And the 3D in near-infrared provides the information about surface of exoplanet. And therefore, we consider that the characterization in near-infrared for exoplanet is essential, no doubt, as presented in many presentations in this conference. An exoplanet discovered by HWO's visible coronagraph can be good target of near-infrared characterization spectroscopy. Next, please. Okay, however, the inner working angles that is a problem. There are enough target. This is a famous website of the target star. For example, we assume frequency 1.8 micron telescope diameter 6 meters. Then lambda over t is 68 milliseconds. Here, and if we inner working angle of coronagraph is 3 lambda over t, there are only 9 observable targets based on this website. And if the IWA is 2 lambda over t, the number increased to 32 observable targets. And if we can realize 1 lambda over t coronagraph, there are many observable targets. Therefore, the development of coronagraph with small inner working angle is very important, of course. And however, such development is very challenging. So we consider that we should also be prepared for the possibility that only the development of normal means 3 lambda body inner working angle would be successful. Next, please. Okay. Next issue is sensitivity. Can we sense enough target? And we started the calculation of sensitivity based on the Renaissance 2024. And today we cannot show very much calculation result, but we found the knowledge, understanding that not only in our working angle, but also sensitivity is severe limiting factor of the observation. And usually, a coronagraph with wavefront control works only in one wavelength standard. Polarization also needs to be considered. Then, much longer observation time is needed to cover the entire near-infrared or visible wide wavelength region. And otherwise, simultaneous exposure by multiple hardware channels is needed. But having multiple hardware channels may conflict with mass, size, and budget constraints. Therefore, we consider how many hardware channels should the HWO program can have is important issue. And in this conference already, good result of ESC is presented. It's important. Okay, next, please. Okay, this slide presents dedicated observation plan for characterizing small number of very nearby targets. Constraints of both inner working around angle and sensitivity are severe. And however, both of these constraints are relaxed in observation of very small number of very nearby targets. If such targets host the second Earth, it will be an ideal target of dedicated characterization. And we think its role is similar to the TRAPPIST-1 in science of transiting exoplanet. Dedicated characterization will be achieved by multi-band spectrum and monitoring observation. And we believe such good target can be discovered by HWO's visible coronagraph. Next, please. This is our voluntary, Japanese team's voluntary study for result of study of entire coronagraph design. And here is telescope light here, and then finally complicated optics here, and finally camera and the spectrum. Next, please. Okay, this is the last slide. How separate is the visible infrared coronagraph hardware? This is important because the top slide is minimally shows minimum separated case of hardware, and the bottom slide shows maximum separated case of hardware. And the important issue of trade-off between observation efficiency and resources. Also, important to define international work sharing of hardware development. Especially assumed science objective, survey plan, target list, and the instrumental design are tightly coupled. And this is always important for any instrument, but coronagraph especially tightly coupled. So the Japan team would like to contribute to this issue via international collaboration. And the team of Japan and JPL have started recently normal regular meeting with JPL team with the FENS team recently. Okay, next slide. Thanks for listening. Thank you.
Thank you, Anisan. Any questions or comments, anybody?
Hi, thank you for interesting talk. So I'm not too familiar with how chronographs work, and on that last slide, I saw the minimal separation case and the maximum separation case. My assumption would be we want the maximum, but I'm not sure if that is true. So could you maybe explain what the two different cases are and what would limit one over the other?
Okay. One page back, please. We have the advantage of this one. Okay. Advantage of minimum case is hardware is simple, compact, maybe money, small money is this one, mass and volume and money is big money we need it, but simultaneous observation is possible. So performance is better. Please, one more point. The scientific viewpoint, performance is also a good contributor there and achieving this number. Right. Okay, thank you very much.
Thank you. Any last questions? All right, let's thank Anisan again. Thank you. Okay, our last speaker of the day is Ricardo Landman for David Dolman from Esron, who's going to be telling us about vortex chronographs. Thank you.
Check. So good afternoon, everyone. My name is Ricardo Landman. I'm an instrument scientist at Nova Leiden University, and I'm also presenting on behalf of my colleague David Dolman at Esron and the rest of the Suppress team. And I'll be talking about phase-apodized vortex chronographs. So one of the main goals why we're all here is because we want to see images like these from the Habitable Worlds Observatory, where we can see an Earth-like planet in the habitable zone of a sun-like star and search for possible life in its atmosphere. Let's give some requirements on the scientific capabilities of the telescope. So like we've heard many times this week, we need exquisite contrast, 10 to the minus 10. This requires chronographs that are nearly optimal with high throughput, small inner working angles, while still reaching deep contrast and being robust to residual aberrations. It's also preferable for the chronograph to facilitate focal plane waveform sense. Next, we would like to search the planet for biosignatures. And for that, we want to search for a lot of different molecules and different wavelengths. And for that, we need a chronograph that works broadband, so over a large wavelength range. And finally, if we search for example, ocean glints or rainbows in the atmosphere of the planet, it would be preferable if the coronagraph has integrated polarization techniques, so we get a polarimetry of the planet. Next, please. So one of the leading candidates for coronagraphs on the Habitable Worlds Observatory is the vortex coronagraph, and I will be talking specifically about the vector vortex coronagraph. So what is that? The vector part is that it uses polarization, manipulation of the polarization of the light to apply geometric phase to the incoming beam. Geometric phase means that the phase, the shift that is applied to the incoming wave is independent of wavelength, so it's achromatic. So we can cancel out light for different wavelengths. So this has the advantage that it's broadband, and because we are already working with polarization, it's easy to include polarimetry in the coronagraph. The disadvantage is that if the coronagraph is not a perfect half-wave retarder, that part of the light does not get the vortex phase imprinted on it, and some light leaks through, and that can mess up the dark zone. Second, the vortex coronagraph is very good for nice circular unobstructed apertures, but when you have a segmented aperture, it loses its performance. I will get back to these two limitations later, how we can solve them. Next, please. So we specifically manufacture vector vortex coronagraphs using self-aligning liquid crystals. So we work with a Japanese company, Coloring Japan, to manufacture these coronagraphs. And their technology has two unique capabilities. One, that we can directly write arbitrary phase patterns. So we can design whatever phase pattern that we want, and that we can write these patterns. Next, by stacking multiple layers of these self-aligning liquid crystals, we can make it work over very large wavelength ranges. We have developed coronagraphs all the way from the optical to the mid-infrared, and this allows for broadband diffraction efficiencies close to 100%. So as I've said, we've developed many different chronographs for ground-based instruments. The latest one that we finished is the one for EOT METIS in the mid-infrared, and now we're trying to get this technology ready for space-based high-contrast imaging. So for this, we have the SUPPRESS project. Don't ask me what the acronym means for peace. This is an ESA-funded project to improve the technology readiness level and the space qualification of this technology. And on the bottom right, you can see some of the vortex coronagraphs that we have manufactured. So we set up a development program with Coloring Japan. They have visited us in Leiden, and we have visited them a couple of times. So here you can see me working in their clean room to improve their manufacturing capabilities, because we really had to make some steps in order to reach the strict requirements for example, the Habitable Worlds Observatory. So there's two main things that we needed to improve. One is the polarization leakage. So as I said before, if it's not a perfect half-wave retarder, some light leaks through, and it messes up your dark zone. So we've now developed what we call a recipe, or a manufacturing method, where we can obtain less than 0.5% leakage over 25% width, and we hope in the coming months to improve this to a 10%. Next is how accurately we can actually write the phase patterns that we want. So here you see the fast axis error, so sort of the phase error that we imprint for a vortex pattern, charge 6 vortex, and we reach an RMS fast axis error of about 0.7 degrees, and it's significantly better than we initially had. Next slide, please. Next, we wanted to test if the technology, the liquid crystal, can actually survive in a space environment. So we did a space environment test at the ESTEC facility from the European Space Agency, and we successfully exposed it to the different tests, and we found that there was no impact on the quality or the transmission of the optic. So this will be tested hopefully soon, really in space, as it will be part of the Toleman space mission as well. Next slide, please. So these are some very preliminary results that I got a couple of days ago of the first vortex chronographs at the THT2 band in Paris, where you can see that we can actually remove some of the starlight. However, there are some ghosts and the leakage, and we definitely still have to improve the manufacturing at test. But that's what we're working on at the moment. So we're still currently manufacturing new coronagraphs for us, and we keep iterating, measuring, and improving again. Next slide, please. So as I said before, there were two limitations, one being polarization leakage and the other being the segmented aperture. So I first want to get back to the polarization leakage. So I said before that our goal is to get the polarization leakage down to 0.1%. 0.1% is nowhere close to the 10 to the minus 10 that we need for the Habitable Worlds Observatory. So how do we still get this very deep contrast? For that, we can use a trick using the multi-grating vortex coronagraph. So what we do is we have our regular vortex, but we also have polarization gratings. These polarization gratings, so if we assume that we first have one polarization state, the main beam gets 99.9% of the main beam gets the coronagraph phase and gets diffracted off axis. While the leakage, 0.1% of the leakage goes through. Then we have second grating, flipped, not flipped actually, but that diffracts the main beam back on axis. Well, for the leakage term, 99.9% of the leakage term gets diffracted off axis. So here we have 0.1% of 0.1% of the leakage. So then you have 10 to the minus 6 already. Next slide. You can repeat this trick one more time, so you're going to make a triple grating vector vortex coronagraph. And then you can actually reach this 10 to the minus 10 requirement for polarization leakage. So we're manufacturing these at the moment, and they will be tested soon at the DHT2 bench in Paris. Next slide. So the second limitation was segmented apertures. So the vortex works very nice if you have this unobstructed aperture where you can see that the star is nicely dimmed and we see the planet. Next slide. If we put the EAC1 pupil, for example, in, diffraction from the segment gaps leaks through the coronagraph and you get a lot of light where you would expect to see a nice dark hole. Next slide. We can solve this, as is known for many telescopes, using apodization. So we can either use amplitude apodization or phase apodization. So we chose to use phase apodization because it has the advantage that we do not remove any light. We don't block any light, we just give it a different phase shift. And the disadvantage of phase apodization generally is that it's chromatic, because phase is dependent on wavelength. But using these geometric phase plates, we can actually apply achromatic phase to the incoming beam. So we can, by using both the phase apodizer, the geometric phase plate, and the vector vortex, it can actually work for both polarization states simultaneously, and we can obtain very broadband solutions. So it allows for a very large bandwidth. Next slide. So this is some very idealized simulation for ESA1 of the Habitable Worlds Observatory, where we can see that we can, with the apodization, we can reach very deep contrast, while it only has very minor impact on the throughput. Next slide. So we developed a first prototype of this, where we increase the segment gaps just to illustrate the effect a little bit more. And you can see an image of the prototype between cross polarizers on the right. And on the left here, you can see the focal plane image after a charge 6 vortex. So on the left, you have the image without the apodizer, where you see diffraction effects from the segment gaps leaking through the coronagraph. And on the right, if you put the apodizer in, it nicely blocks up, reshapes the PSF such the vortex actually works well. So then you get a nice dark zone. Next slide. So to conclude, liquid crystal, self-lining crystals are a unique technology that are very promising for coronagraphs and space-based high contrast imaging. And we are working really hard to improve the manufacturing capabilities and the technology readiness level of this technology. So the main two limitations of the vector vortex coronagraph, polarization leakage, and segmented apertures can be solved, but we still have to do lots of work to improve the manufacturing capabilities to reach the requirements for the Habitable Worlds Observatory. Thank you for your time, and I'll take any questions.
Matt Volker, Goddard. You mentioned the geometric phase plate lets you use both polarizations. You don't mean for the vortex mask, right? You just mean the geometric phase plate works on both polarizations.
So what happens is the geometric phase plate applies the plus phase to one circular polarization state and minus phase to the other one. And it flips the polarization state. So we have right-handed circular polarization, it gets plus phase, flips, and then it gets minus charge vortex. For the other thing happens for the other polarization state, and it can work for both polarization states at the same time, and we don't have to do any polarization filtering.
That's great. Two other questions. So one is, you're using the direct rate on the over of them, right? So have you thought about adapting the profile to compensate polarization dependent aberrations coming off the pupil?
That's an interesting suggestion. I've not thought about that.
That would also be great.
So you mean that you shift the 0 point so that it applies a different phase for the one polarization state and different for the other?
Yeah, so there's a polarization dependent aberrations coming off the pupil for these off-axis designs, especially if they get more compact. And that's one of the things driving the size of the telescope. So if one idea that has been floated is to create polarization compensators, and if you could direct write that into that phase appetizer as well, that would be dual purpose, basically. But that's just one thing. My second question is, again, given that you're direct writing, have you thought about ways to maybe integrate the equivalent of the low order wavefront sensing path in a different way than picking it off at the LEO stop?
Definitely, yeah, that's definitely possible to include. You can do all kinds of optimizations to include use parallel light for wavefront sensing to frag it away, so we can use the sensor to sense it. We are completely free to design a pattern however we want to redistribute the light, so that's definitely possible.
Any other questions or comments? Anything online? All right, in that case, let's thank our speaker again. Thank you. Okay, that ends today's session. I do want to give a big shout out. Oh, go ahead. Online?
Actually, no, hang on. Oh, it's no battery. I have an announcement which is related.
I'll bring it
Yeah.
back.
Okay, I can project. I'm a singer. Okay, right.
I have a service announcement for tomorrow for people that leave and check out tomorrow to go to the airport or wherever. We don't recommend that you leave your bags here, just leave them at the hotel because there's not enough space for all the bags. And so they cannot necessarily guarantee that your bags will be supervised.
Okay, thank you. I do want to thank Stephanie De La Massa for your running of the program. Thank you very much. And let's thank all of our speakers in today. Thank you.